what's your favorite battery management tip that you give to your friends? Mine was definitely don't charge overnight until they added software to like do it for you, but so now I have to find a new one.
Yeah, definitely not to use your phone when it's hot. I mean, your iPhone usually will shut down if it gets hot enough, but even like if it's slightly warm, that will have a very big impact on the on the phone performance. Of the cell performance, but phone as well.
Hey everyone, welcome to It's a Material World. We're the show that uncovers why material science will change the world. Consider subscribing and hitting the like button down below. It would really help us out a lot. Also, we created a free career development guide for MSCs, which you can access using the link in the description. Now let's get on to the episode.
Our sponsor today is Johnson Matthey, a global leader in sustainable technology. Johnson Matthey's vision is for a world that's cleaner and healthier, today and for future generations. Johnson Matthey's scientists use their deep understanding of materials, surface science, chemistry, and chemical engineering to design catalysts, advanced materials, and processes, tackling the world's biggest challenges, such as reaching net zero, enabling cleaner air, improving health, and using our planet's natural resources more efficiently. Johnson Matthey, inspiring science, enhancing life.
Special thanks to MatMatch for sponsoring this episode.
All right, hello everyone. Today's guest is Rachel Carter, a research engineer at the U.S. Naval Research Laboratory. Her work focuses on investigating ways to expand the lifespan of lithium-ion batteries while also pursuing alternatives such as lithium-sulfur or sodium-sulfur batteries. Throughout her career, Rachel has accumulated 53 publications in the field of energy storage, as well as 3 patents. Her accomplishments were recognized by a globally recognized science journal, Nature, where she was named one of the 5 early career researchers in material science. So congratulations on that, and thank you for joining us today. And we're excited to talk to you about batteries.
Thanks for having me.
Yeah, I think a good place to start will just be the basics in defining what exactly a battery is. You know, we remember the redox reactions from our chemistry classes, but maybe you can give us a high-level explanation of how we've been able to capture chemical reactions and make them do electrical work.
Yeah, so basically what a battery does is it harnesses the charge balance required to complete a chemical reaction. So even in spontaneous chemical reactions, the elements ionize and electrons are produced and then neutralized. So basically in the battery, we just designed a system where we can harness those electrons in an electrical circuit. And so what we do is we separate the reactants into positive and negative electrodes. These are referred to as the cathode and the anode, and they are mounted on what's called current collectors, which are used to transport the electrons in the form of current. So when we think about a typical battery in its charge state, when the reactants are stored in the anode, that's the higher energy electrode. And this produces a energy mismatch where the anode is at a higher energy than the cathode. And so as the reactants desire to move towards the lower energy cathode state, we pull electrons off of the negative electrode or the anode. And then to charge the battery, we just reverse the behavior where we actually flow electrons or current into the anode, and that causes the reaction to reverse, and the reactants are returned to their higher energy state in the anode.
I guess just one question that we have about that is that when we talk about batteries with the different poles and everything, there's a lot of different form factors. Like you have your AA, and you have like maybe your phone battery and all these other types of batteries. It might be a little unintuitive to think that they're all the same mechanisms, but I guess can you just confirm that they are, and like maybe how do they differ between the different form factors?
Yeah, so form factor, as you mentioned, has a lot to do with the application that we're using the battery. So the volume constraints or the geometrical size. But the way that we use the same materials is by this mechanism of putting the anode or cathode onto a current collector. So that's just usually a foil, like an aluminum foil that you'd use in the kitchen. And basically what's most commonly done is the active materials, or the anode and cathode materials, are mixed up like a paint in something called a slurry, and then painted onto those foils. And then those now are electrodes that are just configured into the form factor. So the most conventional is the cylindrical cell, much like what you're saying, like a AA, but also lithium-ion batteries are in this form factor as well. And so these foils are just wrapped up and stuffed down into the can, where in a shape like for your phone battery, you have these just layers of those foils stacked on top of each other. So fundamentally, the electrodes are exactly the same. It's just how they're assembled into the can or the packaging.
And generally, what materials are used for like the anode, the cathode, and the electrolyte?
Yeah, so for lithium-ion batteries, the anode is graphite, which is formerly what was in pencil. So the reason why graphite is really effective is because of its layered structure, which I think we'll get into a little bit later on. And then on the cathode side, you have a lithium-containing metal oxide. So the first cathode compound that was developed was lithium cobalt oxide. And there is a decent amount of discussion over these materials now as we're moving towards cobalt-free batteries or trying to use different lithium sources. And so then some of the other more common cathodes now are what are called NMC, so nickel, manganese, and cobalt blends. So they're blends of these different oxides. And then the electrolyte are carbonate-based solutions with a lithium salt.
I guess going into that, one of my favorite battery facts that I know is that the inventor of the lithium-ion batteries is still alive and doing research today. So batteries really, where we see them today, it has been a very fast evolution on this one type. And so if we look back in history, we've only ever seen like roughly 7 different like groups of chemistries for batteries. So it could be like your lead acid battery in your car, what we've been talking about with the lithium ion. And there's like some others like nickel, cadmium, and other such chemistries. Could you elaborate more on the history of batteries and how we reached the point at where we've kind of settled on lithium ion as the majority use of all batteries?
Yeah, so I agree that it's really inspiring for me in particular. I often go to meetings where the inventors of the lithium-ion battery are present, and they're still doing research in the field, which is pretty cool. And so I think I'm going to focus a bit on the lithium-ion battery in particular in answering this question. So as you guys will most likely know, the 2019 Nobel Prize went to the inventors of the lithium-ion battery. Those of us in the battery field feel that like this was long overdue. So the first lithium-ion battery was commercially available in 1991. But this was a progression of almost 20 years of research from the 3 inventors that were awarded the prize. So I'm just going to give a little bit of background about them because I think they're really fascinating. So Stanley Whittingham was working at ExxonMobil at the time, and this was really motivated by the beginning of the fossil fuel crisis in the 70s, where even Exxon itself was interested in how we can look at alternative energy sources. So he invented the concept of the lithium-ion battery. And then after him, Dr. John Goodenough was actually really fascinated by Whittingham's work. So they actually, so Whittingham had gone to Oxford for his PhD as well as his other education. And Goodenough was working for the government, but the government was not yet funding projects based on alternative energy. So he actually took a tenured position at Oxford to do this type of research. And he identified the lithium cobalt oxide compound that I previously mentioned as a more effective cathode than the compound that Dr. Whittingham had discovered. And that was in the 80s. So then about 5 years later, Akira Yoshino in 85 was working for Sony, and so his motivation was really lightweight items, and so he actually replaced the lithium metal anode with a functioning the graphite anode. And so this did several things. It increased the safety of the system, and then it also allowed for these lightweight portable electronics. So there's 3 things I'd like to really emphasize about this. So there's 3 men of different nationalities from Europe, America, and Asia. And not only that, but they had different disciplines of study, so physics, chemistry, and chemical engineering. And also we're in different career paths, the fuel industry, academia, and electronics. So I think this really speaks to how cross-disciplinary batteries are, and this fact is only increasing more as we look at large battery systems and future battery chemistries. So yeah, the lithium-ion battery that, as we know it from 1991, really hasn't changed that much in 30 years. And scientists still look at the periodic table and can identify maybe higher energy materials or more abundant materials, but the realization of a battery that is as cyclable as a lithium-ion battery has yet to be done. So it's really an amazing invention.
Yeah, that's super fascinating. And it's a good point that you bring up the diversification involved and the interdisciplinary aspect of it too, to ultimately create such a meaningful application. And so I was just curious, why did it take so long, up until 2019 for the Nobel Prize winner to be, involved with batteries?
Yeah, I'm not entirely sure. I mean, I know there's a lot of politicking involved with the Nobel Prize. There's lots of kind of some like touring involved, and people advocate for scientists that they believe deserve the prize. But of course, I'm biased. I feel that the lithium-ion battery really changed the world. So it was a very proper award for the inventors.
Yeah, for sure. I think you brought up a really good point too, is that we really haven't strayed that far from NMC and graphite within battery systems. There are a few outliers, such as Sila Technologies, that are starting to put silicon in their graphite, but they are very few and far between. So would you say that most of academic research is into new novel chemistries or ways to make batteries cheaper or more safe, etc., like improving the system we have or creating a new one?
Yeah, I think this is a really great question, and I think it even emphasizes the range of jobs or types of work that can be done on batteries, because there is no one fix-it-all. I think we need a diverse type of different batteries and strategies to really meet our energy storage requirements. So this is going to mean, new and different batteries, better methods to use the batteries that we have, ways to recycle batteries, second life use, and yes, like better controls. So research is being done in all of them, is what I would say. I would not actually even say that there's a prominence of one type of research over the other.
Interesting. So I guess then, I mean, you focused on the history of lithium-ion batteries, and I was just wondering, has the majority of the research been focused on that, and what makes lithium-ion, more unique and more efficient than other previous iterations?
Yeah, so great question. I hinted at this a bit, but what really sets the lithium-ion battery apart is its recyclability. So for portable electronics, this is why the lithium-ion battery really revolutionized, energy as we know it, because we all pretty much carry lithium-ion batteries with us now. Previously, something like a portable electronic would use AA's, which are a single use, or an alkaline battery. So now we can recharge many times. And this chemistry, because of its lightweight nature, where things like lead acid are just too heavy for electrification of transportation, has resulted in the development of, battery-powered trains, cars, planes, all of the above. And then also, as we look towards the implementation of renewable energy, we need load leveling and peak shaving for our grid. So what really sets the chemistry apart is its intercalation mechanism. So it exists inside, it has a host structure that really creates a extremely repeatable process.
Cool, that's fascinating. And I know we'll get into intercalation mechanisms later on in this episode. But one major issue with batteries and lithium ion batteries is the safety side, as we saw with the Samsung phones. And so an interesting fact is battery fires can get up to 2,000 degrees Celsius, which is mind-blowing. And so I was just wondering if you could talk to the root cause of battery fires and how can we make batteries safer?
Yeah, definitely. So most of us probably, when we were talking about the periodic table in chemistry, saw a demonstration of alkali metal being dropped into water. So sodium or potassium makes this bright blue flame. And so this is often what people think of when we talk about lithium battery fires. Although conventional lithium-ion batteries never have metallic lithium in them. The very first battery that Stanley Whittingham produced did have metallic lithium, and this was its biggest concern. And that was the advancement that Yoshina brought, was the replacement of that lithium metal with a carbon anode. So in the lithium-ion battery, we really only have lithium ions, so ionized lithium and not metallic lithium. But what does happen is the carbonate electrolyte is flammable. So when the battery heats up for any number of reasons, whether it's just external heating, an impact, or short circuiting due to a defect in the battery, then the electrolyte heats up, vaporizes, and becomes flammable. And then this causes what we refer to as thermal runaway. So it's a cascade of reactions involving all the components of the battery. And the most energetic of those is the cathode material itself, the metal oxide. And once it catches on fire, it results in those extremely high temperatures, greater than 1,000 Celsius. So very dangerous.
For thermal runaway, right? I think that we've all seen videos of, like, for example, the Tesla car that caught on fire like 6 different times. And that root cause is basically there's still electrolyte and there's still cathode in the system. So going forward, is there any inkling about how we're going to try to curve thermal runaway? Like, once it starts, is there any way we can stop the battery from continuing to run away?
Yeah, so we actually know a lot about this runaway reaction or cascade of reactions. And so we can use things like battery data to identify hints of these types of failure modes onsetting. We can also design around the failure mode. So there's a lot of work being done on what's called propagation resistant designs. So if one cell were to catch on fire, you prevent that failure from going on to the other cells in the pack. So I think a Tesla has something like 9,000 cells. So that's why you see this reignition behavior. But one cell alone is not a catastrophic event. And then also there are strategies, as you alluded to, doing something like fire extinguishing, but very specific to this type of battery or type of fire. And so there is a lot of work being done on the materials front, as well as sort of the control side and packaging.
Interesting. Yeah, I remember doing like a year of research in solid state electrolytes, and that was kind of tying at the safety side of things, just as potential replacement for the more volatile liquid electrolyte. One question actually for David, I was just wondering, I know you're a cell engineering intern. Are you focused more on the safety side or the performance side or something else?
Something else entirely. The project that I'm working on is the dry battery electrode. So like Rachel was saying before, is that we've kind of all split up into different groups amongst ourselves. And so one of the biggest questions for electrification of the entire US fleet is, how do we either build enough batteries and how do we make it cheap enough to where it could be affordable compared to diesel-powered cars? And so one is the dry battery electrode, which I think during battery day could save like 30% per gigawatt hour. So like huge savings because I guess the basic synopsis is if like what she said before is we created a slurry, which is basically we put powder in a solvent and then paint it on. If we could just avoid the solvent and just put powder straight onto a foil, then we would save like 24 hours of heating where we try to dry off the solvent, and we reduce our footprint by like 75%. And so this just means that we can fit more modules in the same space, as well as being faster. So all this would cut the costs. And so that's the big project that we're working on. But within Tesla's, there's so many different other projects, like different materials, as well as learning about the chemistry. And one of the best things that Tesla does is the battery system management. And so making sure that we have individual data on each cell to understand how we should charge it. And so they charge each cell differently depending on where it is in its lifetime, are all revolutionary things that are really helping lead into the future.
Wow. Yeah, that's crazy. I know Elon would be very happy with that, cutting cost by 30%. Or is that right? 30 cost by 30% or something else?
Yeah, so on battery day last year, they were trying to cut the cost of a gigawatt hour by 50%. And so dry battery electrodes make up like 20 or 30%, I think, of that 50% that they're cutting.
Oh, wow. That's crazy. All right. We'll stop interviewing you now, David. We'll go back to interviewing Rachel. But yeah, I think we were talking about solid state batteries. So go ahead, David.
Yeah, so just like you said, one of the biggest things is safety. And one of the leading ideas for safety is the idea of solid state electrolytes, where companies such as QuantumScape are trying to create it for cars to create the safest possible thing. Because a lot of the issues are when a car gets in a crash, how do we protect the batteries from indenting in on themselves or other ways that would lead to the thermal runaway? So could you explain what is a solid state battery and what benefits they hold over one with a liquid electrolyte?
Yeah, so basically a solid state battery replaces the liquid electrolyte with a solid. So instead of a solid, liquid, solid system, it's solid, solid, solid. And so this provides a few different benefits. We can return to the use of lithium metal at the anode because of the elimination of the liquid electrolyte. And then the use of the solid electrolyte does not have that flammability problem. So thermal runaway is at least looks different. Batteries can still be prone to catching on fire, but we're looking at much higher temperatures necessary for the cascade reaction, making the behavior much less probable. So, this is a really desirable configuration. I think it brings a lot more material challenges because you have these solid interfaces, which are very difficult to make ideal. And so now we run into just new challenges where liquid is easily penetrates into solid. Here we have to figure out how to penetrate solid and solid effectively. And also solids are tend to be less conductive thermally and electrically. So we really have to play some nice material games to achieve the same energy storage capability of the solid, liquid, solid system.
Interesting.
I know
Go ahead, David.
Go ahead. Oh. I'll give it a second to cut. All right. Yeah, I know that I do academic research in solid state batteries, and it's almost in a completely different mechanical system. And so the things that we cared about for liquid cells, like how much like solvent or electrolyte or like what's the ratio, kind of get thrown out the window when we look at completely different metrics such as stack pressure, which is you want to apply pressure to the entire cell to get better interface connection. And so it's like using the same two electrodes, but now it looks completely different because you're changing the thing in the middle. So it's very interesting and something that needs a lot of work.
Yeah, I was wondering, so I remember also doing work with solid state electrolytes, and we were making coin cells, and the conductivities just didn't reach the same levels as the liquid electrolyte counterparts. And so based on what David was saying, different set of challenges. Is there like an expectation or like a timeline for when they might be able to like match that same performance level, or are we still a long ways away?
Yeah, I think I can't speak to a specific timeline, but I will say that I think it's not going to happen as quickly as maybe, the articles online may suggest. I think there's a lot more challenges that remain.
Yeah.
But I think it'll happen.
Well, I'll keep my fingers crossed. But yeah, so another cool, I guess, application for this is conversion-based chemistries, or just a research focused on batteries. And this is kind of what we were talking about with the intercalation reactions, where lithium ions are held within a matrix of the anode material, but they don't react with the material. So could you give some more background on intercalation mechanisms and explain the benefit of conversion-based chemistries, and maybe even kind of explain the opposite side, like the challenges that we're currently facing?
Yeah, definitely. So conversion batteries are something I'm particularly interested in, so I'm excited to talk about this a little bit. So I like to use this analogy of friends going on a camping trip at a cabin. So let's say that you're going to a cabin with 6 or 7 rooms. You have 10 friends. So the way that an intercalation chemistry works is each ion or friend has a very particular place that it should be stored in the home or host in the system. And so if each person kind of arrives in a slow increment of time, they can easily arrange into their proper location and do the converse when they're leaving. So this is what, then you have this really sound structure that's hosting these people and providing them shelter from the elements and, maybe even like each other. But, you have to, the host is a really large structure compared to the size of the people being stored there. So a conversion chemistry like really collapses this host or structure material. So then you could kind of imagine like all 10 people laying in sleeping bags on the ground. So there's a lot less footprint, weight, all of these things needed to accommodate the people that are being present in the location. But then you run into issues like environment, maybe, the elements, things like that. And so these types of systems, although they are much lighter weight, lower volume, there's a lot more challenge with keeping the ions the way that they start in the system as they begin. So this is why recyclability is a big challenge. So like lasting for many, many years and many, many cycles proves very challenging for these types of chemistries. So there's some trade-off whether we use conversion batteries for different applications where maybe the lifetime or life cycle is less important, or also, maybe meeting in the middle with some sort of lower profile scaffold, but still providing some rigidity to the reactants and things. So the reason why the intercalation chemistry remains king is that it has this robust storage mechanism. But as we think about really small, lightweight batteries, and we push the envelope, we have to get creative on how to keep the materials in their optimal performance, but also at maintaining their lightweight integrity.
So probably the most famous example of a conversion-based reaction in lithium-ion batteries is probably the silicon in the anode. Could you potentially go into more depth about how that plays a role and what that system looks like?
Yeah, so for the conventional anode, the graphite anode, since the carbon is very layered, so I kind of mentioned like the graphite pencil, so you're literally scraping off those layers when you write with that pencil. And so what we do with lithium ions is store the ions in between the layers, and the layers stay there. But when we put in some silicon, whether it may be the whole anode or part of the anode mixed with carbon, the lithium metal alloys with the silicon. So it spontaneously reacts with the silicon and produces, I think you store something like 4 or 5 lithium ions per 1 silicon atom. So that's an extremely high storage rate compared to the carbon, which only stores 1 lithium per 6 carbons. But because of that, you can imagine how much bigger the lithium silicon compound would be than the silicon compound itself. And so you get things like cracking and delamination of material because of this volume expansion behavior. So that's what's difficult of harnessing that of that reaction. But again, we can do things where we make composites of the materials and kind of maybe leverage what's good about the carbon and what's good about the silicon. We can also use polymers to help accommodate the volume expansion and make it more versatile. So yeah, these are some of the material tricks that are played with that.
Interesting. Yeah, I was just about to ask what kind of materials developments are happening to address these challenges of like harnessing and also like the recyclability. But I guess you were talking about it's like either composites or like polymers or things like that, right?
Exactly.
Cool.
Yeah, and a lot of also surface to bulk. So looking at, nanostructuring of silicon and different structure types. So whether it be nanowires or nanoparticles or more complex nanostructures.
Yeah. Cool. The last new technology that's currently being worked on is replacing lithium with sodium in energy storage applications. I actually interned at a company that focused on utilizing sodium instead of lithium, so I do know some about the benefits and challenges, but we would like to ask you what you think are the largest benefits to switching to sodium, and what are the reasons that the market is almost completely lithium today. And then finally, one thing that we haven't touched on is alkali metals in general. So why is sodium the next choice, and what's the next choice after that, and why is it so linear in our choices in the field? So sorry, that's a lot. So
yeah, maybe I'll start backwards. So when we pick battery materials, we have this amazing map, the periodic table. So we know that the materials on the far left, or the alkali metals, are the most reactive with the materials on the far right, which we typically think of as our cathode materials. And so that's just based on what ions they form and their propensity to form those ions. So the alkali metals, which are on the farthest left of the periodic table, form a 1+, and they're very prone to doing this. So they like to be in the ionized state. And so lithium is the smallest of these, which is why it's the most popular, because that makes it the lightest weight, and therefore it packs the most energy. But that also makes it reactive. So that's one of the reasons why we're intrigued by sodium, because it is bigger than lithium, making it a little bit less reactive. It's also extremely more abundant. So we have like literally oceans full of this stuff. So it actually behaves very similar to that of lithium. So we can leverage a lot of the research that's been done on lithium ion and virtually drop in sodium ion. Although, because it is a larger ion, there are some things that are different. We deal with volume expansion again, as we talked about a bit with silicon and some of the others. Mm-hmm. So we have to accommodate the volume expansion challenges and change some of the electrolyte components and things like that. Mm-hmm. And so these batteries, because sodium is a larger ion, they have less energy than lithium ion batteries, only about 2/3 that of a lithium ion battery. So you can think where in Teslas, we're already talking about the entire chassis being made up of batteries. It just wouldn't be possible to do the same thing with sodium-ion batteries, which you would need, a third more of them.
Yeah.
But what is really exciting is when we really look towards using more renewable energy. So when we do modernize our grid to have solar and wind power, which is an intermittent, a lot of people don't realize that we can't fully leverage these renewable technologies without batteries, which help us have a more produce the energy on demand. So we basically store the renewable source and then deliver it using batteries at whatever time they're needed. So sodium can help us produce the massive quantity of batteries that would be needed for this. We're already running into material limitations for lithium ion because the demand is so great. And so we don't want to create a new fossil fuel challenge. So there has been quite a bit of investment on sodium ion batteries, and I think they will be the next battery that we see penetrating the market to a substantial degree.
Yeah. One interesting point about sodium is that, like you said, I think it's like 22.3 times more abundant. But the biggest challenge I think it's solve is definitely the quantity, because I went to a talk once and they said that we would have to mine almost 50% more lithium each and every year until 2050 to meet the demands that we have to have today, which is just like a crazy mind-boggling fact that lithium just is amazing and has a lot of great uses. But for things just like simple storage, we definitely need other methods, or else we won't ever be able to go fully electric.
Completely
so
agree.
I think you did a great job highlighting that. One other thing that I wanted to talk to you about is when I entered the company, the big thing was like, how do we pack sodium in? And so you said that for carbon, there's 1 lithium to 6 carbons. For sodium, you just said that it doesn't pack, but you have a number to kind of give us a overall feel for how much larger it is.
Yeah, so interestingly enough, the sodium will not store in between the layers of carbon in the way that lithium does. So we, again, kind of have to play some material games. The most common thing that we do is just kind of mess up that graphite. So we make it a little bit less ordered and make these gaps in between the carbons larger. And so in that way we can get something like 1 sodium per 8 carbons. So getting pretty close to the same behavior as lithium. But we also have analogs like silicon that alloy with sodium, and these are tin and phosphorus. And so there's a lot of research going on in using those materials instead of a carbon anode for sodium, because those tin and phosphorus are not as expensive as silicon, for example. So it fits along the goals of the sodium-ion battery.
Interesting. Yeah, all I remember, I guess, in the world of sodium, I remember in my AP Chem class, we did like a sodium bucket challenge. So dropping just like a tiny bit of sodium into water, and then the bucket flew like 30 feet in the air. So all I know is that it packs quite a punch. So I'm curious to see how it'll, make its way into the battery world.
Yeah, so that's what I was alluding to earlier when I was talking about, alkali metals. There is often this demonstration in your Gen Chem class about alkali metals being flammable. But again, the sodium-ion battery will not have sodium metal in it. It'll be ionized sodium. And then another thing to note is that's particularly unique with sodium compared to lithium, is that we can do something called 0-volt storage, which isn't possible with lithium-ion batteries. So lithium alloys with copper, which is our most common current collector material, but sodium does not. So we can replace the copper current collector with an aluminum and use aluminum on both sides of the battery. And this allows us to, for example, ship the batteries in their fully discharged state, which eliminates some risk to, there's actually a lot of risk in the shipment industry for batteries. These massive pallets of batteries, for example. So, nobody wants to get your iPhone in the mail and it's not charged yet, but there's also some benefit to doing things that way. So.
One of my favorite things in lab is that we're responsible for disposing of lithium and sodium. And basically, we have these scraps of lithium that has been heavily oxidized, so it's not even pure metal anymore. And when you put it into water, the way it just dissolves, it just gets, it basically just like catches on fire and blows up. But so the important part is that you can only put in about like this much lithium at a time into water. But one of my lab mates accidentally put water into the lithium, and you never want to do that. You want to do lithium in water. And so basically we had a glass of lithium on fire in the lab because she just poured water in it. So it's extremely reactive, and definitely we had lots of trainings after that, but it's still really cool just to throw in a little bit of lithium and see it catch on fire.
It is, yeah. So I think the hallmark of batteries catching on fire gets a lot of buzz. Yeah. But I would like to emphasize that there should never be lithium or sodium metal in these batteries.
Yeah.
It should be ions only.
Yeah,
it's like easily an easy misconception.
Yeah, that's a
but
good
we do use the metallic. Yeah, we use the metallic elements in research a lot because it's in the most pure form.
Yeah.
And then I guess that leads me to a quick follow-up question. So since there's been less focus on the sodium side of things, how does that factor into like the manufacturing costs? And I know it's a more abundant material, but does that translate to the processing costs at all?
Yeah, so as David kind of mentioned with solid state, we have like whole new processes. These are things that like QuantumScape and others have to tackle. But what is really nice about sodium ion, and why I think it will be the next major battery that we see, although it is a lower energy battery, is that it's really, the processing is exactly the same. So everything should just be a drop-in replacement. We're still going to make slurries or make composites, put them onto metals, wrap them up, and put them in a can.
Yeah, interesting. Nice. Cool. So now we can go on to, I guess, the future of batteries. You've kind of covered the past and the present a little bit, and the future is just super exciting, especially from the battery side of things. And one thing, this isn't exactly materials related, but one of the potential largest performance boosts can be seen with improved software. Could you explain how better software can actually lead to better batteries without changing, the materials themselves?
Yeah, I love this question. So we have 30 years of battery data, and especially companies like Tesla have done a great job of aggregating this data. And so we know a lot about batteries operating in different environments like Arctic or desert, being charged fast or slow. So one of the best things that we can really do is make the battery behave in a way that it wants to, as opposed to how we want it to behave. So you may have noticed one of the things that Apple is really doing this a lot. You may have noticed sometimes now you'll get an alert on your phone when you plug it in at night that your battery is going to charge over the next 6 hours instead of its typical 1 hour. So that's going to really improve the lifetime of your battery. And Apple is actively doing things like this with software updates. So is Tesla. So as we look towards fast charging vehicles, they have a really good sense of how these kind of desirable but maybe not optimal charging protocols affect the battery. So if you do a fast charge on your car, you'll later get a prediction on how many more times you could do that, so that you can at least plan for, if you were going to do road trips and you wanted to do fast charging, you could plan for that. But you should know that it's much better for you to do your typical charging at home on your home charger, as opposed to trying to use the convenient fast charging mechanism regularly. So not only this, but we can, change the rates of the charge, the rest times, or like, how long we've waited between using the device since it was charged and things like that. So This is a very active area of research, and I think there's a lot more to be done with big data and machine learning for batteries as we use them even more.
So yeah, I guess just a quick follow-up, because you mentioned it, was the biggest hurdle is for EVs. How do we match basically the charging time of a gas car, which is just 5 minutes at the pump, for a Tesla or any other electrical vehicle? And what you're saying before is just like, we like it when batteries have their time to figure out the best method to slowly let electrons in. And so I guess you said that right now we know it's a problem, so we give you a prediction of how long you can do this and how many more times, but what innovations are being worked on to completely solve it? Or will this forever be an issue that we will just have to grapple with in the future?
Yeah, so I think there's a couple of good strategies. I'm going to kind of go back to my cabin analogy. So if we tried to fast charge, and so everyone arrives at the same time and they're just running to find their room.
Oh God.
Maybe like multiple people end up in the same room, and like the best room is empty and things like that. So this is why this is the time that the host strategy is the most challenged. Mm-hmm. So as you mentioned, the battery wants to do things nice and slow, put things where they belong, and it will last, forever and ever. But we can do some material strategies. So maybe, aligning the hallways so that the ions can reach where they need to go more effectively. Or decreasing the distance to the current collector, or like the distance to the rooms, for example, so that things can still remain ordered even though it's done at a faster rate. And so this is a material strategy, basically changing the thickness of the slurry coating, or adding like pillars into in the lateral direction as opposed to just the axial direction. Things like that. So these are some of the strategies. And then also back to sort of smart charging strategies, we can do some current ramping. So maybe start with a slower current, pick it up, and then maybe bring it back down a bit, because we know at certain times in the charge, the ions like to move more than other times. So we can leverage these understandings to get a more effective fast charge.
Interesting.
Yeah. In research, we do things at like C over 50, which means that it takes 50 hours to do one charge. So I don't think, and that's like when we're trying to get like a perfect performance, and even then, like these new chemistries don't work. So I can only imagine if people would be pretty bad if it took 2 days for you to get one charge of your car. So it's really cool to see how much faster we can push.
Yeah, I remember, literally over like the past 5 years, David has like countlessly told me like how to improve my phone battery or my computer battery. It's like, don't leave it like plugged in all the way overnight if you can like,
Apple's fixed it for you now. I preach this as well. I also like tell my friends not to use external battery packs, but they're pretty much the norm now. I just suggest getting a high quality one. Mm-hmm. Some of the others will they'll use really high currents and things which are detrimental. But
yeah. I guess, what's your favorite battery management tip that you give to your friends? Mine was definitely don't charge overnight until they added software to like do it for you, but so now I have to find a new one.
Yeah, definitely not to use your phone when it's hot. Your iPhone usually will shut down if it gets hot enough, but even like if it's slightly warm, that will have a very big impact on the phone performance. I was gonna say cell performance, but phone as well. And then if you happen to be in a cold environment, don't charge it. So yeah, maybe it's sort of specific scenarios, but are important to consider. You could think of like definitely, hot car or cold car scenarios where these might be relevant.
When I first got into battery research, it's like a baby. It doesn't like get too hot, it doesn't like get too cold. And one of my favorite examples is that one of my roommates, whenever it was below 40 degrees outside, if he pulled out his phone, it would just instantly die. And so it's because he would leave it at 10% or less every single time, and he would charge it and then still be next to the charger and then just unplug it when it got to 10%. And I was like, what are you doing? So that's how you don't take care of your battery. But yes, anyway.
I love that story because like you are so passionate about batteries and he does not care at all. He doesn't care about he handles it so poorly. But I guess that did remind me of a question about how weather affects car batteries. Like any general tips from like, let's say like a Tesla in, northern Minnesota versus like the dry heat of Arizona.
Yeah, so the cold is definitely a bigger challenge, as David kind of mentioned. And that's just because ions slow down when they're cold. So you get transport and conductivity challenges at low temperature. So if there's any possibility to charge in climate controlled environments, that would be optimal, whether it be maybe a heated garage or something like that. And then as far as hot, oh man, yeah, I think, the heat scares me as well. But yeah, I think just definitely pay attention to be extra sensitive to those warnings. If your car is overheating, take a break, because you don't want to be in a car that's catching on fire.
I know for a fact that Tesla ACs their battery pack to keep it colder, and so basically whatever you find comfortable, the batteries will also find comfortable. So it gives the AC as well to keep everything.
That's true. They do. I think the biggest concern is actually the edge cells, which may be more exposed to like the roof of the car or something like that, because they're more prone to a temperature variance compared to the pack. But all of the car companies provide thermal management to the cells, and particular cooling. I think soon enough we'll also see heating to them as well. But so like GM, Ford, Tesla, all of the above.
That's interesting. Yeah, I know it's a much smaller scale with our phones. If it's overheating, we just kind of get like that notification and we let it go for a while and let it cool down. But, much more potential, safety situations if it's for a car. But yeah, we can move on to improving battery performance via like microstructures to aid in more repeatable reactions. And I was just wondering if you could delve into what exactly is being done on this frontier.
Yeah, so basically, this is actually probably one of the material strategies that's nearest to my heart, because this was what I did in my graduate research. And so this is often termed like scaffolding or structure design, nanostructure design. So I've mentioned current collectors a few times because they're the most important aspect in harnessing the electrons or the electrical current produced by the reaction. So we can do these sort of 3D current collectors. So, you can imagine some sort of foam-like structure that's interconnected and can deliver the current to the circuit. And then that is hosting the active material throughout. So you get surface area benefit as well as, greater interconnection, and that provides for higher rates and other desirable features. There's actually a startup called Pietro Battery, which does something like this. I believe there's maybe another few. 24M is doing something like this, where their slurry material is almost a scaffold in itself. So it has these networks of conductive materials that are aligned through really thick paint layers or slurry layers. So there's a lot of really unique strategies here, and these methods are being looked at also for solid state. So first starting with a complex 3D structure of your materials and then putting down the solid electrolyte around that scaffold. And that helps increase the interface interconnections and conductivities and things.
On the microstructure side of things, when we talked about conversion-based reactions earlier, one of the largest downfalls, but not all of their downfalls, is that the large volume expansion where when you alloy, your silicon crystal, for example, will expand by like 4 times. Has these microstructures been looked at as a way to almost contain the growth where like potentially there's more room on the inside for it to grow to make it more repeatable?
Yes, exactly. So often the silicon may be stored inside a carbon structure that can accommodate some, it has some more flexibility to swell and shrink and things. And then the silicon, although it may crack or, move inside that structure, it's still relatively held in the course of the whole electrode. So this goes from, pretty rudimentary designs where you're still just sort of mixing the materials together to really sophisticated, lithography-based designs where the electrode structure is carefully considered and developed, and this can take several days to produce. So we have to balance, cost and scalability of the designs that we're looking at. So oftentimes research goes very high performance, so maybe something that's really difficult to produce, but it does perform well.
Yeah.
And then we'll kind of go a few steps back and figure out how to harness the same mechanisms in a system that's scalable.
Okay.
So you mentioned that balance between like costs and needing high performance. So I was just wondering what kind of applications could like scaffolding be used for in the future?
Yeah. So I think sulfur batteries are among the most prominent that use scaffolding. I think silicon to date is still being used in a really low percentage. So something like 10% silicon added to a conventional carbon anode. And kind of as I was mentioning, you just hope that the carbon helps the silicon stay in the electrode as you would like it to. But sulfur batteries in particular, sulfur is insulating by nature, although it spontaneously reacts with lithium or other alkali metals. So you need a conductive interconnection in this. So we use a scaffold basically of carbon. We make a 3D structure of carbon, put the sulfur on that carbon, and the carbon plays several roles. It accommodates the reaction, which involves a volume expansion, and it also transports the electrons to the sulfur and away from it. And there's several sulfur battery companies that are using carbon scaffolding currently.
Cool. Well, we covered the immense importance of batteries in society and how they will only become more important in the future. However, like we said, there's always still more things to overcome and things to figure out. So considering everything we talked about today, what advice do young want to enter into the energy storage space?
Yeah, I'm really passionate about this question. I've found that we already have a huge labor shortage in this topic area. And as vehicle companies are really trying to move manufacturing, particularly to the States, and as our demand for batteries increases globally, this is only going to increase. So I've also alluded to the fact that batteries are extremely interdisciplinary. So whether you worked in electrical engineering or material science or chemistry, even math, computer science, you can really make a big impact in this field. And I think it changes our quality of life, whether we're using portable electronics for our own, personal desire, AirPods or whatnot, or trying to really, change the world and use renewable energy. You can imagine that it's really fulfilling to work in this field. So a piece of advice that I really try to give myself often and give others is to try to figure out what you like about your job. And this can mean many different things, even for students. So what is it that you really feel your full self when you're doing that? Is it like working in a team, or conveying your results, advocating for what you did, optimizing an experiment or the software that's running the experiment, writing the report, also maybe building a widget that's going to improve the test flow or the performance of the system. So yeah, lots of different areas of interest, and I think just trying to figure out what you really like to do and how can you do more of that thing. So that's what I would like to say.
That's great. As someone who's also in the energy space, I would just say, like what Rachel said, is just there's so many different things, and so there's numerous problems. And lithium-ion batteries have only been around for 30 years, and when you think about all the other inventions that are like common day, almost it has enabled so much of what we use now, like phones, iPhones, laptops. All these different things are now completely different because of it, but there's still so much work to be done to fully understand it, because in the grander scheme of things, 30 years isn't the most time to figure everything out. So there's always more work to be done and always new chemistries to discover. So, yeah.
Completely agree.
Yeah, absolutely. Well, thank you so much, Rachel, for joining us today. I know I learned a lot. I hope our audience will learn a lot from this. And you shared a lot of valuable advice in addition to just sharing kind of the history of batteries and the future of this field. So we really appreciate you joining us today.
Thank you. Thanks for having me. I really enjoyed it.
Thank you for tuning in to this episode of the It's a Material World podcast. If you enjoyed the show, consider subscribing, hitting the like button down below, and commenting what topics and guests you'd like to see next. To download our free career development guide for MSCs, check out the link in the description. We'll see you soon, and in the meantime, go change the world.